All right, today we're going to look at doing some calculations regarding a hypothetical wooden block which has a weight of 20 newtons. It's on level surface, which means it also has a normal force of 20 newtons. It's being pulled along with a force of 8 newtons. There's a few things that we want to calculate. Well, let's keep in mind first what else we know. We know that it's a wooden block, and we know that it's a wooden surface. I don't know if anybody wrote that down when they sort of copied down the questions and thought, well, that's important to know too. Wood. It is. It's essential that you sort of kept that in mind as you further what's impossible. Right? That it's not impossible, but if you don't sort of think through it like this, then you quickly hit a dead end and you go, this isn't possible. Because it wasn't, but it is. But it's not. So we were asked to calculate what is the force of friction, what is the net force, okay, what is the mass, and what is the acceleration. So 4 calculations. If we assume that, this is being pulled along at constant velocity, then we know, just like yesterday, the pull force equals the friction, this is 8, the net force is 0, the mass is just like whatever, it needs to be. This is mg, so just divide this number by 10, so it's about 2 kilograms. The acceleration is 0. That's if we assume it's constant velocity, where the acceleration is 0. And we can't just assume that. We can't just say that makes it easy, okay? But it's the only sensible thing to do if you think to yourself, well, it's not impossible. I got to be able to do something here. Okay, so if you start to think about how would I calculate the frictional force, do it in the order that they suggested. It's like we're not going to assume that this is 0, and then be able to just say, well, this equals this, and then the net force is 0, and the mass will just calculate independently. We need to think about an equation for this, and so we're going to write out what we know about friction. Frictional force is equal to the coefficient of friction times the normal force. The question really is expecting you to either look up on a table of values what is the coefficient of friction between wood and wood, or to have done some lab work before in your life where you'll know you can make a claim about this. That's the key to this question. Did you do the lab work yesterday? And you'll know this, and then you have to plug it in. So this has to be like a research value or an empirical value. They're expecting you, like they told you it was wood and wood for a reason. Because you could look up on it in the table, hey, yeah, what's the coefficient of friction between wood and wood? We did it for ourselves yesterday, right? And so I'm going to use just a value of 0.3. Okay, and really you could, like you could queue up a resource and see sort of a table of values for different coefficients of friction for all sorts of different surfaces. I'm just going to use the 0.3. The normal force is 20. So the frictional force is, what is 0.3 times 20? 6. So that's going to be my answer. It's a frictional force based on what the coefficient of friction is. And you need to sort of either use your lab value, the claim that you made. Now, if I use 0.44, I would get the unfortunate situation where there's more friction than pull force, right? Like the value I think I concluded yesterday based on my data was 0.44. Well, 0.44 times this is like 8.8, I think. And so I'd actually have more friction, which means that it would be decelerating. It's almost like, let's say you're pulling something along at 8 newtons, and then all of a sudden the friction acting against it is more because you pull it into some sandpaper or something like that. Well, what's going to happen? There'll be a net force this way, and it will decelerate, right? So like if its motion is this way, but the net force is that way, that just means it's braking, it's slowing down, it's decelerating. So it's okay for the frictional force to be greater than the pull force. It just means that either it's at rest, it's not moving, right? Because like as this marker sits on my hand inclined this way, there's a component of its weight that makes it want to go down this way. But the fact that it doesn't slide that way must mean, there's more friction going this way. So when friction is greater than like the propulsive force that makes it want to go, it's just going to stay stationary. Like you need to have enough of the weight, let me do it this way. You have enough of the weight acting so that overcomes the friction. Right, so eventually, like, if you know there's friction between that surface and my hand, there's so much of the weight acting down that it overwhelms the friction. So we're going to redo this lab next week with inclined planes. We're going to put the block on a ramp, lift the ramp up until it slides down. So how much of the weight does it take to get this thing to go? So once you have a value for the frictional force, based on what you decide the coefficient is, it should be reasonable based on wood and wood, okay? And you can look it up. Maybe it's like 0.3, it's around it, 0.2, 0.3, 0.4, really depends on the type of wood. The net force then, 8 minus 6. Okay, that's how we do this. So this is where we talked about how do I solve problems using F equals MA? And I said sometimes students forget to add up the vectors here, the vectors. And so I have an 8 Newton vector minus a 6 Newton vector because they oppose each other. So this is negative relative to that way. So I have a net force of 2 Newtons. 2 Newtons equals mass times acceleration. In order to calculate the acceleration of a 2 Newton force on a given mass, we need to know the mass. Well, we know the weight is 20 Newtons because they told us, I forget if they tell us, oh, it's a 20 Newton block. They told us the weight. And that's how we knew the normal force was this. That's how we knew to plug it in here, right? Because friction relates to the normal force. Can we just make G10? I guess it's going to make a G10 here. If we bother anybody, but 9.81, it must be every time in this class. Okay, fine. Use 9.81. I'm going to use 10, okay? Hopefully that doesn't bother you too bad. If G is about 10, right? 9.81, let's just call it 10 for the purposes of this calculation anyway. Then the math is much easier, right? 20 divided by 10, that's 2. No, it needs to be 2.1, whatever, say, fine, look at that. Not a big deal. So if G is 10, which is not exactly 10, but the math like then this thing is about a mass of 2 kilos, which means now we can go back and solve for the acceleration using this, right? Using F equals MA. So according to the coefficient of friction, which I think is reasonable, the frictional force here is 6, which means the net force is that taken away from 8, the pole force, so 2 Newtons of net force, of resultant force. So 2 Newtons of resultant force acting on 2 kilograms of mass, meaning an acceleration of 1 meter per second squared, right? 2 times 1 is 2. And so that's how we have to go about these calculations, all right? Not assuming that it's being pulled along at constant velocity, but by knowing what the coefficient of friction would be between the surfaces. So the clue in this question really was the thing that's the least sort of likely. I think, the clues in physics questions are the numbers, the units, it was these words, wood, right? But you have to think about it specific to the surfaces, right? Your claim should be something like mu for wood and wood is, right? And that's the slope of your best fit line. So if you haven't already finished that, work on it tonight. I'll do tomorrow for spring term 2, but also think about spring term 1. Credit aplusphysics.com, the problem set dynamics friction for this question, question 17 through 20 of the next problem set. And we'll see you next time.